Hello everyone. In this video we will be analyzing a T-beam, a given section using the limit state design. So before solving an example problem, let us see what are the different steps involved in analyzing a given T-beam. So first, in the step 1, for the given sectional dimensions and AST, need to assume the depth of neutral axis is lying within the flange. That is the first case. So we are assuming that, and the second step will be finding the depth of neutral axis. So in the first case, the depth of neutral axis is given by this equation. So this equation is similar to the singly reinforced beams finding depth of neutral axis. So this equation we will be using it, and we'll get what is our depth of neutral axis. And once we get the value, we'll be comparing it with the depth of flange. If this is if xu, that is depth of neutral axis, is less than the depth of flange, then the assumption is correct. Then we need to compare the xu value, the limiting depth of neutral axis. So that is nothing but xu max over d, which can be found in class 38.1 note, page 70. So after comparing, we need to compare it with the xu limit, the xu which we obtained, and we need to distinguish what type of section it is, whether it is under reinforced, balanced, or over reinforced. After distinguishing, we need to find the ultimate moment of resistance. So the ultimate moment of resistance is found out using this equation. So if the case 1 is correct, whatever assumption we have considered for case 1, that is correct, then we can find out what is the ultimate moment of resistance. So in the case if xu value is greater than depth of flange, then whatever case 1 we have assumed that remains invalid. So in the case 2, find out the depth of neutral axis, we are going to use this equation. So here, if you can see here, we have a new parameter which is yf. Yf is given as 0.15 xu plus 0.65 df. This equation can be found in IS code 456 on G 2.1 clause, page number 97. And once we get the xu value here, we need to verify whether your xu is lying within the 7/3 of df or greater than 7 divided by 3 df. First is we need to check this. So if xu is lying within the 7/3 df, then we need to find out the moment of resistance using this equation. This equation is given in G 2.2.1, page number 97. So here xu value whatever we got here, we need to substitute that along with the effective depth, and we know the width of the web and width of the flange and yf. So substituting this, we will be getting this moment of resistance. And in a case after getting the xu value from here, if xu is greater than 7/3 df, then we need to use the following equation. The only change which from this equation is df. And along with that, we also need to find out what is xu. Xu can be found out using the same equation here. The only changes here is capital Df instead of yf. So from this we will be getting the new xu value and moment of resistance. This is how you need to find out the moment of resistance for a given section. This equation is available in the same clause G 2.2, page number 96. Now let us see an example. So this is the example. Determine the ultimate moment of resistance of an isolated T-beam having a span of 6 meter and cross-sectional dimensions as shown in figure, assuming FCK equals 20 MPa and grade 415 steel. So this is the T section which has been given. You can see that width of the flange is 900 mm, effective depth is 600 mm, and depth of flange is 120 mm. There are 5 bars of 25 mm dia, and width of the web is 300. So these are the given: df equals to 900 mm, df equals to 120, bw equals to 300 mm, d equals to 600 mm, fck equals to 20 MPa, and fi equals to 415 MPa. Now, with the number of bars given, let us find out what is the area of tensile reinforcement. That is nothing but F into pi by 4 t square, that is 25 square. So this is giving me a value of 2454 mm square as a AST. So let us assume the step 1. Let us assume that our depth of neutral axis is lying within the depth of flange. This is case 1. So we are assuming that. In the case 2, we need to verify whether the assumption is valid or not by using the depth of neutral axis equation. So xu is equals to 0.87 f by ast over 0.362 fck bf. So once we calculate this, we will be getting this 136 mm. So this equation, it is available in IS code in page number 70 in clause G 1.1. Okay. As you can see that the xu calculated is greater than the depth of flange, that is 120 mm. So whatever assumption we have made, that is not valid. Hence, we will moving to case 2, that is xu is greater than df, and we are presuming that xu is also greater than 7 over 3 df. Now, as per this case 2, this is the equation to find out what is my xu value. So we will be having this yf here. Yf is nothing but 0.15 xu plus 0.65 df. Solving those equations is give rise to the xu value as 158.2 mm. Okay, and once we get the xu value, when you substitute that yf equation, you are getting 101.73 mm. Now, if you see xu is greater than depth of flange, that is 120 mm, and along with that, whatever xu we got, that is less than 7 over 3 df, which is nothing but 280 mm. So whatever assumption we have considered, it's valid. So we can derive or find out the moment of resistance as per the case 2. So before moving find out the moment of resistance, let us see what is find out the compare it with the limited depth of neutral axis. So we already know for Fe415 it is 0.48 xu max or xu limit by d. So when I substitute the value, I am getting 288 mm, which is less than, which is greater than, this is actually greater, which is greater than xu, which we have got here 158.2 mm. So hence this section is under reinforced. Now to find out the ultimate moment of resistance, this is the equation. So the equation is available in the IS code G 2.2.1 page number 97. So substituting all these values along with the YF, which we have got 101.73, we are getting the ultimate moment of resistance as 4.82 into 10 to the power 8 Newton mm, which when we divide it with 10 to the power 6 converting into kilonewton meter, it is 482 kilonewton meter. So this is how you analyze or find out the ultimate moment of resistance of a given T section. So with this I will conclude the video. Thank you.